we are going to look at proof. Some of these things, that the proof one might be on an exam. Really thought 2 years ago when they had the first exam that for sure they were going to put a proof question on there because it was a new topic, and then they didn't. I have to double check last year if they had a proof question on the exam or not. Problem solving, which is part of the toolkit, you get hit with that all year, right? Every time I give you a take-home quiz, does it have like crazy problem solving questions on there? Yes. Where it's like, oh, this is a statistics question with logarithms. Or we had the probability question with infinite geometric sequences. So you get this problem solving all the way along. We're specifically going to look at modeling because a lot of you might like to use a modeling idea for your IA. It's a really, I like it for the IA because it's really easy to hit a lot of the things in the rubric that you can make an IA that's not that hard to write, that fits everything in the rubric so that you can do well. And if you're like, this essay writing is stressful for me, well, let's do a modeling one. It can make it less stressful, but maybe it doesn't. The hard part about how it's marked, the IA, is that it's marked on mathematics and personal engagement. So if you choose something that you're really interested in, sometimes finding the mathematics that works is hard. So then you lose marks in the mathematics section. If you find something that fits really well with the mathematics section, they're like, I can tell this isn't something you're really interested in, you just did this because it's an IA, then you lose marks. Like, they make it so you can lose marks in one section or another, and it's very hard to get both. But sometimes that happens. And there have been papers that have scored 19 out of 20, 18 out of 20. Really, really good papers in the past. I'll show you some of those as well. Plus, we're going to look at technology in here, how you can use your graphing calculator or Desmos or other programs to make models and get equations. Okay, so starting off with proof. A deductive proof. Deductive proof uses information that you already have, and then you logically show how something else has to be true. Okay? This is very similar to what you did in identities. You had information, you changed things, and you deduced, or you went from one place to another place to prove something. Some new symbols. Okay? Yeah. IB questions, you know those show that questions? You might have had some in your labs already that you have to just demonstrate that two things are equal. That would be a deductive proof. Okay? We've got an equal sign. Here's a new symbol. A 3-line equal sign. That is to show an identity. You didn't use that in identities in grade 12, but that is a new symbol. Ooh. This seems like this shouldn't be something that you should prove. It should be something that you just know. But whenever you're trying to prove something, you'd be like, okay, I split it here. I don't know that this is true yet, but what do I know? I know how to add fractions. I can add fractions by getting a common denominator. So on the left side, I could change the 1/4 to 3/12. 3/12 plus 1/12 is 4/12. I know how to reduce this. And just like an identity, we prove this is true. And it almost seems that this isn't a real proof because it's just arithmetic. But technically it is. You have showed that the left side is equal to the right side, and it's always true that 1/4 plus 1/12 is 1/3. Okay? Not too bad, right? There we go. What about this? Could you prove that 1/m plus 1 plus 1/m squared plus m is equal to 1/m? So now we're into algebra proof. Well, the right-hand side is a single fraction. How would I add the left-hand side together? I would need a common denominator. Now, in finding that common denominator, maybe I want to take an extra step. Can you see that you could factor the bottom of the second one? And so when I'm trying to get a common factor, well, this one is missing the m on the bottom, so I'd have to also multiply the m on the top, and I would get m, right? I have a common denominator now of m times n plus 1, and on the top, I have m plus 1. That, of course, these factors are the same. They would simplify. And I just showed that 1 over m plus 1 times 1 over m squared plus m is always equal to 1 over m. Now, this was algebra. What's powerful about the algebra? Okay? What's powerful about the algebra is if m is 3, we just proved the one we proved before. In fact, this pattern always works. So did you know, for example, that 1 over 6 plus 1 over 30 is 1 over 5? We can now just plug in 5 for m and make a whole bunch of true statements as a result. So the algebra proof was stronger than the number proof. The number proof showed us one specific example. The algebra proof just showed us a whole pattern of things that are always true. And I personally, I love when you take an algebra proof and put it back into numbers and be like, wow, there's so many things I can now quickly add together because I've seen how it works in algebra. Then there's a whole bunch of proofs that involve even and odd numbers. So you've never really done stuff like this a lot before. But we can take and we can make general forms of numbers. Would you agree that even numbers are always 2 times a natural, or 2 times an integer? If you took all of your numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and doubled them, you for sure would get an even number. Odd numbers could just be that you take an even number and add 1, or subtract 1. Both would be fine. But I double something, for sure I have an even number. If I add 1 to it, for sure I have an odd number. Okay? Consecutive numbers. 2, 3, 4 are consecutive because they come right after each other. So if I wanted to write that with algebra, I have m, the next one would be m plus 1, the next one would be m plus 2. So we get these kind of proofs. Can you prove that an even number plus an odd number is odd? Now you could check. 2 plus 3, it's 5. It works for that example. The problem is, how many examples would I have to check? There's also 2 plus 5. It's 7. It works. What about 8 plus 17? It works. But there's an infinite amount of ones to check. So just checking a few and seeing that a few work doesn't prove that it always works. Maybe out there is some weird even number and some weird odd number that when you add them together, it's not odd. Well, if we want to disprove that no such weird even and weird odd numbers work, we would have to prove that any even number plus any odd number is always going to be odd. How would we do that? Well, even number. Where n belongs to all the integers. Okay? So we start with something general. This could be any even number, every single one that exists. And then we're going to let 2k plus 1 be any odd number, where k is any integer. Something to note here, I make sure in this example I use different variables, because if I used n twice, then I would only prove that any even number plus the consecutive odd number is odd. I wouldn't prove that all of them work. I'd only have a specific case. So I have to make sure in this example that I use different variables. What do I want to prove? I want to prove that 2n plus 2k plus 1 is odd. How do I do that? That would be adding them together. This is my any even number. This is my any odd number. If I add them together, I get 2n plus 2k plus 1. How do I know this is odd? Well, out of the first two, I could factor out a 2. Yes. I could factor out a 2 out of the first two. And then you have 2 times something, that for sure is going to be even, right? Wow. What is that? Even. It's a smart board. I had a professor that wrote like this in university. So meticulous and smart. He was a very good professor. When he wrote something on the board, just like enjoyed every letter, how it was shaped, every number. I don't know if he's still teaching at the University of Manitoba. But if you get Professor Maron, very, very good. I'm pretty sure it's right. I remember first class, he also he would be teaching a lesson about this vacuum. And he said, can you hear me in the vacuum? Nobody could hear me in the vacuum. It was like his way of making sure everybody sat in the front. Like the very first class, where do all the students sit? Right at the back, right? Next day, everybody's sitting at the front of the class. Anyways, so I'm distracted here. 2 n plus k would be even, then if you add 1 to that, that makes 2n plus k plus 1 to be odd. And we just prove it. Does that make sense? As we've proven every single even number plus any single odd number is always going to be odd. And we just use the format of the numbers to prove it. some very powerful things with this. Did you know that when you multiply any two odd numbers together, you always get an odd number? If you think about it, kind of makes sense. Like 3 times 3, that's 9. 5 times 7, 35. Seems to work in our heads. But to prove that it always works, right? We take one odd number in that form, where n is an integer, and then 2k plus 1 be another odd number. Where k is any integer. And we have to show that this times this can be written in an odd number format, which is an even number plus 1. So if you multiply this out, can you see that you would get 4nk plus 2n plus 2k plus 1. If you distributed everything. And then out of the first 3, I can factor out a 2. If I factor out a 2, does it make sense that this part is even? Right? So, and sometimes this is the part about these proofs that feels like you're doing a little bit of hand waving, or like it doesn't really feel too mathematical. Like, I can say this is even, so then the whole thing is odd, because I'm adding 1 to an even number. And then we can write a statement. We can write a statement that the product of any two odd numbers is always odd, because we were able to manipulate it algebraically to be the form of an odd number. Sometimes I'll see in proofs like this, sometimes I'll see in proofs something like this, where they go, let p equal 2nk plus n plus k, so p belongs to the integers, because these were all integers, and then you would get 2p plus 1, therefore that's odd, because it's fitting the format. So if we want to show something is odd, we have to show that it's an even number plus 1. If we want to show something's even, you need to be able to factor out a 2 out of the whole thing. And our proofs can get a little bit crazy. This one's not crazy yet, but we're going to get to some crazy ones. Does this prove that any odd number squared is odd? Did we just prove that, or do we have to prove this separately? And this is sometimes the question, is a proof strong enough to prove something else, or does that something else need something different? So the proof that we just proved was that the product of any two odd numbers is odd. Does that prove this? Yes, it does. Because an odd number squared is an odd number times an odd number. We proved any two odd numbers are, which would include an odd number times by itself. So yes, it does. If this came up on a quiz or a test or your exam by itself, the proof would look identical to this, but you wouldn't have to have different letters, right? You could have 2n plus 1, 2n plus 1. And you have any odd number multiplied by itself. When you multiply it out, you would still get a lot of this, where you could factor out the 2 and show that it works. So there are a fair number of proof questions, and I think I have a homework sheet for this that we'll get to in a question. But your textbook has things like this. I don't know if I got this from your textbook or a different one. You be the examiner. The question was, prove that a product of an even number and an odd number is always even. And 3 students provided 3 different solutions. Which one is correct? Or are none of them correct? Or are they all right? What do you think? Good, bad, mostly good, mostly bad? You judge the 3 questions, or the 3 solutions. All right, let's look at solution 1. Okay. Is solution 1 completely correct? Or does it have something slightly wrong? Ideas, thoughts? So what did they do in solution 1? They had it. They had 2n for their even number. They had 2n plus 1 for their odd number. They then distributed just the n part inside, kept the 2 out, which made it 2 times something, which they said that's 2 times k. That's even number. We're good. Does this work? Or is there something slightly wrong? And what is the slightly wrong thing, if there is? They didn't change the variable. So this only proves an even and an odd number if they're consecutive, because the n is the same. So it's not any odd number. It's an even number, and the next number, which is odd, is always going to be even. Which then makes this one better. The only difference between these two is they changed the variable, so then this one would be a better proof. I like the setup that we did before, where we describe what our numbers are to begin with before we multiply them, where I said let 2m equal an even number, 2n plus 1 equal an odd number, so you can sort of see where it's coming from. But this one would be fine. What's wrong with this one? Same kind of problem, right? They're saying this is even. This one also don't like the fact that they're not using the proper form of an even number and odd number. It makes it a little bit more awkward. Sort of like, this one's kind of like, yeah, it works. Yeah, I don't think you know what's going on. Completely. But again, it's using the same variable there. So this idea of having a different variable in there makes that proof. Interesting discussions on generalizations. Sometimes we notice in mathematics a pattern from many examples that makes us believe something is always true. Math teachers teach you this fallacy all through your life. You come to math class. I'm going to teach you about completing the square for quadratic equations. I show you one example, and it works. And I expect you as a math teacher to say, it always works, yay! Which technically isn't always true. In fact, there are some things that seem to be always true, which aren't. And it's like, oh, it always looked at that like that was going to work. Yeah, I did that on purpose, so that you would think it would always work. And then, haha, here's an example that doesn't work. Okay? But as math teachers, we kind of start class by telling you, I'm going to teach you something that's always true. You go, okay, I'm not going to question you, you're the math teacher. And I say, here's example 1, here's example 2. Do you see what's the same? Do you see the pattern? And then you nod your head and go, yeah. And you're like, that always works. And you're like, okay, but that's not a mathematical proof. That's using a couple of examples that makes us believe that something is always true. Okay? So, in mathematics, when we think that something is always true but haven't proved it, in mathematics that's called a conjecture. And there are some famous conjectures that still no mathematician has ever been able to prove, and no mathematician has ever been able to disprove. So we don't know if it's always true yet, but we've never found one that doesn't work. So here's one. Every odd number bigger than 1 is either a prime number or can be written as a prime number plus twice a square number. Which is kind of this is a crazy thing. Okay? For example, 15 is 7, 4 is 2 squared. If you double 4, you get 8, it works out. Let's pick another one. You pick 23. Can we write this as a square number plus a prime number? Or 2 times a square number plus a prime number? Does it work? Look at this. 2 times 9 plus 5 makes 23. Now, this is a nice conjecture because it's not intuitive. You're like, oh yeah, every time I think of 41, I think of 2 times this square number plus this prime number. Okay, well now I'm curious about 41. What would we do for 41? Oh, 2 times 16, 32 plus 9. No, doesn't work. Because 9 isn't a prime number. Maybe we found it. Maybe we have just disproven about 2 times 4. Is 33 a prime number? No, it's 11 times 3. Maybe this is the first one ever, and no one has ever thought of 41. Anybody see one that works? 2 times a prime number. Sneaky. 37 is a prime number. I thought we had found one that wasn't going to work. Could write it to the math journal and say we're the smartest class ever. We found one. Goldbach's conjecture is gone. He's no longer famous. We crushed him. But no, it still works. Okay? Computers have now shown, okay, that they thought this always appeared to be true, but with computers they finally found 2 numbers that don't work. 5,777. We would have got there eventually, right? We were at 41. And 5,993. And up until all the odd numbers to 10 to the 13. Those are the only 2 that don't work. Crazy. So if I was teaching this to a class, I would have basically said, hey, any example you ever find should work. In fact, there's like millions of them that all work, except for those 2. I think that's just a really good example of where something appears to be always true, right? Your first 6,000 examples or 5,005, divide by 2, they're odd numbers only. So first 2,500 examples you try, all worked. That should generally lead you to think, oh, it's going to always work. Because we did 2,500 examples that worked. I'm going to guess the next one's going to work. And how surprising it must have been when someone found this. And they probably thought, I did my mental math wrong. What am I missing? Okay, here's another one. Every even integer greater than 2 can be written as a sum of 2 prime numbers. Okay, so you take 8. By the way, is 1 a prime number?
Yeah, I know.
It is not. So 1 is not a prime number. What are the 2 numbers that add to 8 that are prime? 3 plus 5. What about 4? If 1 is not a prime number, can 4 be done?
1 plus 3.
Well, 1's not. You're not allowed to use 1. 2 plus 2. Sneaky. Now this one, they've now found out there isn't one that doesn't work. And they've gone all the way up to 10 to the 18. But still, that doesn't prove it. As we saw with the last example, there might be some crazy big even number that doesn't work. That's going to be the key to the universe once we find this big even number. I don't know. Maybe, maybe not. So, what some mathematicians do as their job, right? If someone were able to come up with a logical proof to show this, that saves a lot of time, because you don't have to check every single number. If you can show it through a proof that it always is true, you've solved it. No longer have to check any more numbers. But nobody has been able to prove this. And so mathematicians do 2 things with some of these ideas. On Monday, they go to work to try to prove that it works. And they spend all Monday trying to prove something works and get nowhere. So on Tuesday, they come back to work. And on Tuesday, they spend all day trying to find an example that show it doesn't work. And then if they can't find any examples, then on Wednesday, they go back to try to prove it works always. On Thursday, they go back to the end. And on Friday, they finally give up. And they say, I'm a terrible mathematician. But sometimes it's like that. And some crazy, to blow your mind just a little bit, it has been proven mathematically that there exists some things that are true that cannot be proven. They have proven this. I have proven that some things are true that cannot be proven, but I just don't know which those things are. Terribly frustrating. But this might be one of them. This might be one of the things that is true, but we will never be able to prove it. But we don't know if it's one of those ones that can't be proven until we keep trying for so long and get so frustrated and give up. So there's some sort of logic math stuff coming along. Prove that 2n plus 1 squared minus 2n plus 1 is an even number for all positive values of n. So if we wanted to prove this question is always even, what we have to do is manipulate it. Eventually, we should get this to be 2 times something. So how would I manipulate this? Well, I might distribute this and multiply it out. 4n squared plus 4n plus 1 minus 2n plus 1. Combine my like terms, and I would get 4n squared plus 2n, and my 1's disappear. And then I could factor out the 2. And I've proven that it's even. And this will be the last one that we'll do for today. We'll end with this one. We want to prove that if you take 2n plus 1 squared minus 2n minus 1 squared, the answer that you get is a multiple of 8. So how would you show, this is where the logic comes in, how do you show something is a multiple of 8? Would you agree that makes sense? If our answer is 8 times something, then our final answer would be a multiple of 8. If we can't factor the 8 out, then it wouldn't be a factor of 8. So what would we have here? If we multiplied this all out, can you see that you would get 4n squared plus 4n plus 1 minus 4n squared minus 4n plus 1. You distributed and squared those. Then if you combine your like terms, what happens? You just get 8n. So that will always be a multiple of 8. Which is kind of cool because now if you put in a number for n, like 100, 201 squared minus 199 squared is 8 times something. That's a true statement. And things and proofs like this sometimes come up on sort of, I'm going to say math contest questions, where it's like, hey, if you recognize a pattern in something, then you can solve questions that you couldn't solve before. Because not very many people are going to notice, like, right, if someone said, hey, 201 squared minus 199 squared, you're like, I have no idea. But you probably wouldn't think of it to be a multiple of 8. And now we've proven that that's true if the pattern fits this way. All right. Maybe, yeah, other types of, no, I'll save the other types of proofs for next class. We'll end our video here.